In today's lesson, we're going to start our multiple choice review. It's probably helpful for you to know what the multiple choice portion of the AP exam will look like. You will have 28 multiple choice questions without a calculator, and you will have 55 minutes to complete that portion. Then you have a second part, 17 multiple choice questions with the calculator, and you have 50 minutes for that portion. You should guess. Unlike the SAT, scores are calculated purely by number correct. There is no deduction for an incorrect answer, so you should answer every single question on the test. Even if you don't get to those questions, then you should go through and fill in some answers. Please don't always fill in C. We'll talk about smart guessing when we do some practice problems and we talk about, okay, well, what if we got to this problem and we really didn't know what to do? How could we guess? It is smart, obviously, to work through the test completely, all the problems you know how to do first, then go back and pick up the ones that are either more difficult and time-consuming or that you did not know how to do. The test is not arranged in order of difficulty, so question number 28 may be easier than question number 2. So you need to keep that in mind as you're working through, and you want to make sure that you read every single question in case there's an easy one towards the end that you know how to do and can get the points for. Okay, so today we're going to begin our review, and we'll begin our review with limits and derivatives. I often hear from many of you that limits are the things that are causing you pain, so let's see if we can remember what a limit is. A limit is the definition of close to. The idea of close to describes a limit. So a limit and a function value may be the same, but they don't have to be. The limit question is just saying as x gets close to a particular value, what does y get close to? It's fine if y actually equals the value, and it's okay if it doesn't. So for example, if we had a graph that looked like this, and let's call this x value a, then the limit as x approaches a is this y value here. We can call that b. So we would say the limit as x approaches a of my function here, I'll call it f of x, is equal to b. The answer to a limit question is the y value that the function is approaching. There is no function value there, so that gets us to a second concept that's related to limits. One of the related concepts to limits is continuity. Remember that continuity, our kind of working definition of continuity, is that the graph has no breaks. So there is no place where you would have to pick up your pencil in order to draw the graph of the function. Also remember this specific definition, so if we're asked to verify that something is continuous or to show that something is continuous, especially in a free response question, we're going to want to use this formal definition of continuity, which says the limit as x approaches the value that we're trying to determine is continuous of the function has to be equal to the function value. So in order to be continuous, our function value has to exist and it has to be the same as the limit. So if we're asked a question about continuity, we're going to want to write that definition and then start working on the two sides and show that they're equal. Just in general though, if we have a graph or some question where it's calculator active, then we can just look at the graph and we'll know that the graph is continuous if there are no breaks. We talked about a situation right up here in our picture where the graph has a limit but is discontinuous at x is a. So in this situation in my graph here, I do have the limit as x approaches a of f of x, and that's b, that's the y value b, but there is no f of a in the function there. I might have a graph that looked like this, and this is the point A. We'll say this little point is C, and this one up here is B. In that case, f of A does exist. F of A is C. The limit also exists. The limit as x approaches A of f of x is the y value b. My graph's a little off, but that's what it should be. But that graph is discontinuous because the function value and the limit value are different numbers. So again, that's an example of using that formal definition to show that the graph, I would have to pick up my pencil to draw that graph, so that graph is discontinuous. Another concept related to limits is differentiability. We want to make sure we keep these things apart. in order to be differentiable or have a derivative at a particular value, a graph has to be continuous, it can't have a sharp corner, and it can't have a vertical tangent. I think I usually state those in the positive, so I say a function is not differentiable if, and we have three possibilities of ways something is not differentiable, but they're listed there. Here's some examples of limits. We'll do graphical ones first. In my first example here, note the limit as x approaches 5 is 5, looks like. Think for a second about, is the graph continuous at 5? And the answer is yes, it is continuous. We might also be asked, is the graph differentiable at 5? And we would say no, not differentiable at x is 5, because there's a sharp corner there. The way we formally talk about a sharp corner is we would say that the limit as x approaches 5 of the derivative from numbers from the right side is not the same as the limit as x approaches 5 from the negative side of the derivative. The slopes are very different coming in there to 5, and so the way we talk about slopes being different is talk about the limits of the derivatives. So the derivative to the left of 5 looks like it would be positive 1. The limit to the right of 5, numbers bigger than 5, would be negative 1, and those two values aren't getting closer together. In the next example, the limit as x approaches 5, I think I needed a circle here. Hard to get the computer software to draw a circle. So the limit as x approaches 5 does exist. It's still 5, but this graph is not continuous at 5, and if it's not continuous, then it's not differentiable at 5. It is continuous other places, from 0 to 4, 5.4.9 or whatever, and it is differentiable at all those other places, just not at 5. Then our third example here, we have a piecewise function, and we're asked to find the limit as x approaches 1. If I'm asked to find the limit as x approaches 1, I have to check using my piecewise function for the limit on both sides of 1, because 1 is the place where the pieces potentially break apart. So if I want to find the limit as x approaches 1, then I would find the limit as x approaches 1 from numbers bigger than 1, which would be this definition, the x plus 1. And in order to find that limit, I just plug in 1 plus 1 is 1, so that's 2, and we'll review that on the next slide, the algebraic definitions. The limit as x approaches 1 from numbers smaller than 1, I'm using this definition, x squared plus 1. 1 squared plus 1 is 2. These two are the same. So the limit exists, and the function value, f of 1, is 2, and so actually that graph is also continuous at 1. Our limit strategies, so what we just did in that piecewise function, our whole goal with limits is essentially to be able to plug in the x value into some version of the limit question. So the first thing we try to do when asked to find the limit as x approaches a number is just plug in the number. If that fails, then we try to do something algebraic. We try to factor, we try to multiply in, we try anything that we can think of that would algebraically simplify f of x. And then we go back and try to plug in x as a. So our goal is consistently to try to plug in the x value into the function. And we can also, if we have a table or a graph, if we have a calculator active question, then we can certainly consider that as a possibility. These limit strategies, these work for as x approaches a numerical value. We've also seen limits to infinity, and we've actually seen more examples of that since we studied limits than limits as x approaches a number. And we've talked about limits to infinity. It's the same kind of idea. I'm going to not do that. We need to know that 1 over x to the n approaches 0. And then otherwise we just kind of plug in infinity, or think about plugging in infinity, and then think about the effect on the graph. So for example, if I wanted the limit as x approaches infinity of e to the x, I would just think, okay, if I'm going to plug in infinity, I'm getting e which is 2.7 something, to a larger and larger and larger number. So that's going to have an infinite limit, or we can write the limit does not exist. If I were to do the limit as x approaches negative infinity of e to the x, then I'm thinking e to negative 10, negative 100, negative 1,000, negative 1,000,000. That's getting closer and closer to 0, and that limit does exist. Remember that negative exponents make a fraction. Fractions, according to this up here, approach 0 as n approaches infinity. So a couple of examples here. The limit as x approaches 2, so my first attempt is just to plug in 2. If I try that, I get 0 in the numerator and 0 in the denominator. I can't divide by 0. So my second try is going to be to do something algebraic. Looks like I can factor the numerator. There's nothing to be multiplied, so factoring is my only choice, leaving the denominator alone. I can then simplify this fraction and see that the limit as x approaches 2 of that is the same as the limit as x approaches 2 of x plus 2. Now I try again. Can I plug in 2? 2 plus 2 is 4. I sure can, and I have my limit. Question 2 is a limit to infinity, so I'm going to think here, okay, well, as x gets really, really big in the numerator, that 4 is meaningless. As x gets really, really big in the denominator, this 2 is meaningless. So I can think of it as the limit as x approaches infinity of 3x squared divided by 2x squared. My x squareds would then cancel, and I get 3 over 2. And the limit as x approaches infinity, there's no x there, so there's nothing to consider there, and I'm just reduced down to 3 over 2. Then the other thing that we're reviewing in today's lesson is derivatives. This will seem much more familiar, I think, than limits. Remember that derivatives describe an instantaneous rate of change. Average rate of change or average velocity does not involve the derivative. Those are both slope. Derivatives also describe the slope of a curve at a point or the slope of the line tangent to the curve at that point. And then these rules you'll remember. I'm not going to recite them all. I'll just write them for you. But remember that the derivative of the sum or difference of a function, you can just take the derivatives of each, leaving them in the same relationship they were to begin with. If I have the derivative of functions multiplied, then I need the product rule, which some of you know is fig-figgy, so the derivative of the first times the second unchanged, plus the first times the derivative of the second. If I have two functions divided, then I need quotient rule, derivative of the first times the second unchanged minus this time, the first times the derivative of the second, all over the denominator squared. And the fourth operational rule is what we know as chain rule, derivative of the outside, leave the inside alone, times the derivative of the inside. It's important to know these rules and to be secure in them, especially quotient rule and product rule, making sure that you remember what the signs are and all of that. A good bit of the multiple choice questions are very straightforward. Just do you know the basic facts? So you don't want to miss ones that just ask you to find the derivative of something. You'll be very good at those. They don't require a lot of heavy thinking, and they should be almost automatic. So just make sure that you have learned the rules carefully. Don't forget the denominator squared when you're doing quotient rule and that sort of thing. Then we have function rules, derivative of a power function, bring the power down, subtract 1 off the power. Derivative of an exponential, this is the one we tend to forget, so you may want to make a special note of it. Natural log of the base times the exponential we had to start with. Derivative of e to the x is e to the x. Derivative of ln x is 1 over x. Those are pretty familiar because we've just seen them again in integration. Derivative of sine is cosine. Cosine is negative sine. Tangent is secant squared. And this one's not listed, but I'm going to list it. The derivative of secant is secant tangent. You may be asked for the derivatives of other trig functions, so you need to know the relationships. If you're asked for the derivative of cosecant, you would just want to rewrite cosecant as 1 over sine and use quotient rule. If you were asked for the derivative of cotangent, you would want to write cotangent as cosine over sine and use quotient rule. And then don't forget that tangent is sine over cosine in case you're asked to, and secant is 1 over cosine. So don't forget those relationships in case you need to evaluate. So this is a good time for me to put in a close to the end of the year plug for learning the unit circle. Again, you don't want to miss just a straightforward find the derivative of this question because you can't remember what the cosine of pi over 4 is. So make sure that you review your unit circle and that you're confident with that. And then our last derivative rule is the derivative of an inverse function. So the derivative of f inverse is 1 over, and then it's the derivative of the regular function, f prime, evaluated at f inverse of x. So what that means practically, remember that the x value for f inverse is the y value on f. And so if what this is telling me is giving y as an input and getting x back, the x value that belongs on f prime, and then it's 1 over f prime evaluated at that appropriate x value. We'll see some examples of that just to make sure that you can kind of manipulate that. That formula is a little awkward, but it just is what it is. Then we've studied 2 theorems in talking about kind of the first part of the year. These are not both derivative theorems. The second one is. Our 2 theorems that you should know. Intermediate value theorem. Intermediate value theorem guarantees a y value. It talks about a function taking on a particular value. And the way that you use intermediate value theorem is that you want to show, you want to show that the function is continuous. So make sure that you state that. If it's not stated, that's a condition to use the intermediate value theorem. So you would want to say 2 parts if you wanted to use the intermediate value theorem. You would want to say function is continuous. And then the other thing you want to do is evaluate f at the endpoints. So f of a and f of b, find those 2, and show that your value is between those. So in short, what the intermediate value theorem says is that as long as a function is continuous, then it has to travel continuous on an interval, then it has to travel everywhere between f of a and f of b. In order to get from f of a to f of b, it has to travel through every y value in between f of a and f of b. So if my function is continuous on -1 to 2, and I know f of -1 is 0 and f of 2 is 7, then I know y has to take on every value between 0 and 7. It has to get there somehow, and if it's continuous, it can't jump around. The function can't, so the graph has to travel from a y value to the next y value, and so it has to pass through all the y values in between. Practically, though, algebraically, you would want to do those 2 steps. State that the function is continuous and that your value is between. So evaluate f of a and f of b, and then state, oh look, mine's in between these 2. The other theorem that we've talked about is mean value theorem. You want to reach for mean value theorem when you're asked to show that the derivative takes on a particular value, not the function itself, but the derivative of a function. And the mean value theorem rests on the notion of mean, meaning the arithmetic mean, meaning average. So what the mean value theorem tells you is that the derivative, which is slope at a single point, takes on the value of the average rate of change, which is slope between 2 points, at somewhere on the interval between the 2 points. So if you wanted to use the mean value theorem, you would want to calculate 2 things as well. You would want to say that your function is differentiable on the interval. That's your condition. And then you would want to calculate average rate of change. So you would want to find f of b minus f of a over b minus a. And then you want to say, hey, look, my value is equal to that average rate of change. So in order to use the two theorems, the pattern is the same. You need to state a condition, intermediate value theorem, function is continuous, mean, function is differentiable, and you want to calculate something. For the intermediate value theorem, you want to calculate the y value at the two endpoints. You're trying to verify a y value. For the mean value theorem, you want to calculate average rate of change. You're trying to verify a derivative. And then, of course, this should be second nature by now. The equation of the tangent line problem, remember that you always need slope, which comes from the derivative, and you always need a point. You may be given any one of those three pieces of information, the slope or either half of the point, and asked to write the equation of the tangent line. So if you're given half of the point, either the x value or the y value, you want to plug the other half back into your original equation to find the missing one, x or y, and then go through and find your slope. If you're given the slope, you'd want to set the slope equal to the derivative, solve for x, which would give you half of your point, and then go back to your original function and solve for y to get the remainder of your point. So you could be given any one of the three. Just make sure that if you're looking for parts of the point, x or y, you probably are using the original equation. If you are given the slope, or if you're looking for the slope, you're thinking of the derivative equation. That's the difference. We've also talked about that if we're asked where a tangent line is horizontal, then that means the derivative had to be 0. So we would set our derivative to 0 if we're asked about a horizontal tangent line. If the tangent line is vertical, that means the derivative is undefined, which generally means setting the denominator of a rational derivative equal to 0. Most of the time, that's the situation we're in when we're asked for something that's undefined. And then we don't have to, we could do y equals mx plus b, or we can do point slope form. Y minus the y value is the slope times x minus the x value. It does not matter in a free response question which form of the equation of the line you use. Obviously, if it's a multiple choice question, you're going to have to select the correct answer in whatever format they've given you. So you may need to be able to move between the two formats. Okay, that's the end of today's lesson. You should go now and fill in the first part of your review questions. That's your homework, is to go back through and think through the lesson and fill in your flashcards or your study guide sheet, whichever way you're doing those, through as far as you can get. Thanks, and we'll talk again tomorrow.